For this section of Unit 8, we're going to look at some right triangles that contain common acute angles, but not 30 or 60, not 45, so we can't rely on patterns for these. What we're going to try to do is generate a common ratio or a way to find that ratio and apply it so that we can get any missing side length. So the trigonometric ratios are what this overall topic is, and the one that we use in any given problem is going to depend on what information we're given. So as you look at exercise 1, I've already filled in the missing sides here. If you just take your centimeter ruler, you can see how many millimeters each one roughly is. So it's not perfect, but we're getting pretty close to these whole millimeters. If you want to just copy them in, if you have a ruler, you can confirm it. And so in the chart, what we're doing is just entering the data that you get from the measurements and then just doing a quick division on each one. So if we divide side BC by side AC, that's 24 over 42. Get a decimal, 2 decimal places. Do that for AB over AC as well, and do that for BC over AB. And then it's going to ask you to do exactly the same thing for triangle DEF. So just pause and do that for a minute and get those ratios written down. All right, to the nearest hundredth, what we have is as follows. And so all of these are very close from one triangle to the next. If I divide BC by AC, I get 0.57. If I divide EF by DF, I get 0.58. And notice the commonalities in those ratios. BC is the vertical leg, the shortest side of this triangle, and AC is the hypotenuse, the longest side of that triangle. Another 35-degree triangle, if I take opposite side, this vertical leg, the side across from the 35, and I divide that by the hypotenuse, I get something very similar. So the two side lengths within the two triangles, the two side lengths within a given triangle will divide out to the same thing as the common sides in a similar triangle do. And it won't matter what the dilation is. We can make this as large or as small as we want as long as we maintain a 90 and a 35. Those sides will increase proportionally or decrease proportionally by a scale factor. And so the ratio between any pair of sides should stay the same. And as you can see, this data, it's roughly the same. But again, these are rounded numbers. These weren't exact millimeters. So we would expect them to be just a little bit off. But the point is, we're getting roughly the same thing in each case. All right, so if we want to try to summarize what's going on here, if we share a right angle and an acute angle, they're similar by angle-angle. So all of the ratios of the relatively positioned sides, and that's the key right there, relatively positioned, must be equal. They're slightly unequal here because of rounding errors, but they're going to be relatively equal. All right, so using that work from part A, determine the lengths of ST and TR to the nearest tenth. All right, so here's another 35-degree right triangle. So what I know is, in any 35-degree right triangle, the ratio between the sides should be roughly the same. And so what we're saying then is that the ratio between ST and RS, which is vertical leg and horizontal leg, or another way to say it is the side opposite the 35 and the side adjacent to the side to the 35-degree angle. Follow that my cursor here from 35 across to the side that it's not touching. That's considered the opposite side, and the 18 is considered the adjacent side, the one that's touching this angle. If I divide those two sides, I should get the same ratio as any other pair of opposite and adjacent sides in a 35-degree triangle. So this BC over AB, that's what we had up here in this diagram if I look at the opposite vertical side and the adjacent horizontal side. All right, so as long as I'm relatively positioned, those ratios should be the same. So that's what this proportion is saying. And so that ST divided by RS, which is 18, should be roughly 0.7. It came out to 0.71 or 0.69 in those other calculations in the chart. So about 0.7 is what I would expect. And if I multiply by 18, I would get about 12.6. So that's my rounded proportional answer. Likewise, if I want to figure out TR, now I can look at RS and TR in a fraction. Again, RS is the one that I knew, that's the adjacent side. TR is a hypotenuse, so I have to find the same relative pair in one of the other triangles. And so AB over AC in the original triangle represents those same two sides. So I can set the two fractions equal to each other, put the 18 in the RS position. The 0.82 is our 0.83, roughly, whatever that came out to be, is what I would expect this ratio to also divide out to, since it's a similar triangle. So in this case, if I put this 0.82 over 1, I would have a cross product of 0.82 TR and 18 times 1, which is 18. So to get TR isolated, just divide by 0.82 and I get 22. So it's just proportion solving from there. But the point is, if I pick two sides in a right triangle with an angle that I already know information about with a different right triangle, then I can set them equal to the appropriate ratio. All right, next page. So all right triangles that share an acute angle are similar. So we don't really care what the size of the right triangle is. If we know one of the acute angles, we know that we're going to have similar triangles, and then all the ratios will apply. And so these are the three trigonometric ratios that the rest of the unit is going to be based on. It's really, you're going to see these ratios over and over and over again over the next 3 years of your math life. Even if you don't go further beyond high school with it, you will see these over and over again. So these are going to be emblazoned in your memory. So we have sine ratio, we have cosine ratio, and we have tangent ratio. Sine is abbreviated SIN. It is not sin, it is sine. Cosine ratio is abbreviated as COS. It is not cos, it is cosine. And then tangent is abbreviated as TAN. Again, not tan, tangent. We're just going to use those abbreviations in our equation writing. And your calculator uses them as well. So the first ratio, sine of A, means sine of angle A, the sine ratio of angle A, which is that if I'm starting at angle A and I divide the opposite side, the one that's not touching angle A, by the hypotenuse, I'm expecting that ratio to divide out to exactly the same thing, no matter how big or small the triangle is, if it contains whatever degrees angle A is. So let's just imagine for a second angle A is 25 degrees. I could make as big or as small of a 25-degree triangle I want. If I divide those two sides, I should get the same exact ratio every single time. Cosine. Cosine takes the adjacent leg, which in this case is AB, and the hypotenuse, and divides those two. And it's basically saying if I have any 25-degree triangle, or I'm just making that number up, but any triangle that contains the same angle, and I divide the adjacent side by the hypotenuse, I will always get the same decimal. I will always get the same ratio. And so that's cosine. Tangent is when I take the two legs that make up the right angle. So if I'm starting at angle A and I go opposite to BC, that's my numerator. Adjacent to the angle is my denominator. Opposite over adjacent is going to give me the tangent ratio. Now, the reason why we have three ratios is because you never know, first off, what side you're going to be given, and you also never know what side you're going to have to solve for. So we need three different ratios to be able to use any piece of information we're given and solve for any piece of information we need. So in exercise 2, we're just going to quick evaluate these. You're just going to type it in your calculator, find the sign button, type 35, hit enter. If you get 0.57, then your calculator is good. If you don't get 0.57, you need to make sure that your calculator is in degree mode. Your calculator, if you're using a TI-84, would default to radians mode, which is for circle trigonometry and not for triangle trigonometry. So all you need to do is press the mode button and just double check that degrees is highlighted and not radians. That's, I think, the second or third option down in that menu. If you are on a scientific calculator, it depends on what kind of calculator it is. Look for a key that says something like mode, and you want it to say DEG for degrees. If you can't find it, just make a note of it so that you can let me know in class, and we'll make sure you can find it. That's something you always want to check when you're doing trig, because if the memory got reset for whatever reason, either by you or somebody else, you're going to need to make sure it's in degree mode. All right, and so these 35-degree angles are coming out to about the same ratios we got by measuring and dividing in the experiment on the previous page. Now the calculator is storing those ratios so you don't have to measure. And it's doing so because you might want, well, you're going to want different angles besides 35 degrees. And there are tables that will tell you every single angle from 0 to 90. What those ratios come out to, but sometimes you don't even want whole number angles. You want angles in between whole numbers, decimal angles. And so your calculator will give you any angle and tell you what the ratio should be. You'll just use that ratio to figure out what the missing side length is in your triangle. All right, so we're going to get into the calculator extensively throughout this unit, but just a little bit more on sine, cosine, and tangent. I know this video is running a little bit long, but bear with me. It's your first exposure to trigonometry, so I think it warrants a couple extra minutes. As you get good at identifying these ratios, you're going to know how to identify just automatically. But a lot of times, and this is not spelled right. This mnemonic, this word mnemonic is not spelled right. But it's what we're going to use to remember this is SOHCAHTOA, and you just say that out loud. SOHCAHTOA. The SO part represents a sine ratio, and you can imagine what the O and the H stand for. If you're talking about sine, it's the opposite side, and it's a hypotenuse. And not only is it identifying the two sides, it's also telling you what order to put them in. So sine is opposite over hypotenuse. And cosine involves the adjacent side and the hypotenuse, so it's in that order. And so you would make a fraction adjacent over hypotenuse, and that's your cosine. Tangent is opposite over adjacent. Remember the two sides that create the right angle. So start at your angle, go opposite, put that in the numerator. Adjacent is your denominator, so TOA stands for tangent equals opposite over adjacent. All right, so in this right triangle here, give the correct trigonometric ratio, and you could try these. I'll scroll back up so it's not given away right now. If you want to pause it and try these, try to identify them, go ahead and do that. All right, now bringing it back here, if I want sine of angle R, the first thing I have to do is locate angle R, because that's telling me that I'm using a specific angle. So angle R is down here, and from that angle, if it's sine, it's opposite over hypotenuse. So if angle R is my target angle, my reference angle, I guess is what we'll call it, I'm just going to go straight across the triangle, maybe even draw an arrow, and that 5 represents my opposite side, or segment TS, or ST. That's my opposite side. Because it's sine, it's OH, which is opposite hypotenuse, so 13 is my denominator, TR is my denominator. Now, if I switch the angle to angle T, now I'm coming from angle T to get my opposite side, so it won't be 5 anymore, it'll be 12. Again, just drawing an arrow across from that angle will be helpful to you. So 12 goes into my numerator. Hypotenuse is hypotenuse. It doesn't matter what angle you're going from because it's always across from 90. And so 13 remains my denominator in the second sine ratio. When I go to do cosine, RS over RT, because from angle R, it's the adjacent side now. So I want the side length, the right angle side that is touching angle R, that's the 12. I don't want to go all the way across the triangle. And then the hypotenuse is 13 again. So AH for adjacent hypotenuse. Angle T, I'm coming to the other side of the triangle. Adjacent is now 5. Hypotenuse is 13. So 5 over 13. So those are the cosine ones. And tangent is the ones that make the right angle. And you could kind of remember that because a T is sort of like a squared off letter for a right angle. So if you want to remember tangent as the two right angle sides, from angle R, it's always opposite on top. So it's across to the 5, and then 12 goes on the bottom because it's opposite over adjacent. And if I come from angle T, opposite's 12, adjacent's 5, and I have that ratio. All right, let's wrap this up. So could measure of angle R equal 28? Use your calculator and your answers from above to make an argument one way or the other. All right, well, let's just say angle R is 28. If I were to use that sine ratio, then I would expect that sine of 28 would give me the same decimal as dividing 5 by 13, right? Because opposite over hypotenuse. Well, if I type sine 28, I get about 0.47. If I type 5/13, I get about 0.384. So those calculations aren't the same. They're not even really close. And so it can't be a 28-degree angle. And we could keep guessing and checking at it. There's going to be a calculator way to get it quickly, to get what that angle is. But we're just showing that it can't be 28 because sine of 28 tells me what that ratio should be when I divide the opposite side by the hypotenuse. But doing the sides that I have shows me that it's not actually that ratio, which means the angle couldn't have been 28. All right, much more on this in class, much more on this in lessons to come. Please answer your question that's following honestly so that I know what we need to do and what we don't.